Welcome back. Today we're going to talk about series, and series plays on the same kind of patterns as sequences, but with series we're actually going to be doing a lot of addition and looking at some tendencies in adding up consecutive numbers and seeing how that works. So a very famous example of this problem is to find the sum of the numbers from 1 to 100, and there's no calculator allowed. Carl Friedrich Gauss, who's a famous mathematician, when he was very young, his teacher posed this problem to his class, and while all of the other students were busy writing away, after a couple of minutes, Gauss just kind of sat up and said, "I'm done." And the teacher kind of looked at him sort of sideways and was kind of looking at him like, "How could you possibly be done?" And he came up with this slick little trick that we're actually going to play on as we learn about series today in our lesson. And so basically what it plays on is the fact that if I were to add up the numbers 1 to 100, a strategy would be to add them up in this way, right? So I could do 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and so on and so forth. What Gauss did was he said, if I don't look at the numbers in order, if I actually look at them like two sets, what I can do is I can take 1 to 100, and I'm just going to kind of go down the line here, plus 97, plus 98, plus 99, plus 100. And if I look at these numbers and I say to myself, if I add the first and the last, I get 101. If I add the second to last, or the second to last, I get 101. And so essentially what Gauss did was he rewrote the numbers sort of like this. He wrote 1 plus 2 plus 3 plus 4 and so on and so forth. And you can rewrite it in this way. And so essentially what he figured out was that we could add 101 100 times and then divide by 2, because if we use two sets of them, we say, okay, I've got two, I added two sets and I got the full sum, and then I divide by 2 and I end up with 5050, okay? And so the sum of a sequence, that's a summation. So sum of a sequence, right? That's what Gauss did. Actually, 1, 2, 3, 4, 5, 6, so on and so forth, that's actually just a sequence, an arithmetic sequence where you add 1 each time. And so there's a way to notate this, and the sum of a sequence, and the sequence is going to be defined by this: a1, a sub 2, a sub 3, a sub 4, etc., right? All the way up to a sub n. And when we do the sum of the sequence, we're going to use a special notation. That special notation is this big Greek letter sigma. And the notation looks like this: k equals 1 of a sub k. And so here's how it works, right? So this would literally be read the sum of a sub k from 1 to n. Okay? And so down here, this is where you start. And this is where you finish. This defines each term. That doesn't even look like the word defines. Defines. And so the just rote, get down and do it way to do this is to find every term. So find the first term, the second, the third, the fourth, the fifth, and add them all up. And you can use that nifty little shortcut that Gauss used. Or we've got a couple little shortcut formulas that we can use. But first we're going to do a little work here to that end. So let's find the sums. I didn't actually draw these in because I want to practice with you drawing these mathematical symbols. Here's the first one. Sigma. And we're finding the sum of a finite, meaning a certain number of terms. Right? So that's like, it's got 6 terms, it's got 7 terms. It's not an infinite sequence. We'll talk about that in just a minute. And the number, so I've got this here from 1 to 5 of 3k. So what that literally means is I'm finding 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. And my top number tells me where to start, so that goes here, right? And then my end number goes here. So I'm literally finding every one of those terms and adding them all up. Well, when I add all those up, I've got 3 plus 6 plus 9 plus 12 plus 15, and I've got 9 plus 9 is 18, and this would be 40, and this would be 55. Did I do that right? 9, 18, 30, 45. You guys are like, this guy teaches math? Okay, that's the sum of the first 5 terms of this defined sequence here, and there's a finite number of terms because I only have 1, 2, 3, 4, 5 of them. Okay, the next problem is a variation on a series problem, and it says this: a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? Well, there's a couple of different ways to do this, and you could easily draw a picture or find a pattern. I'm going to show you. So we've got 8 in the first row, then 10, 12, 14, 16, 18, 20, 22, 24, right? You find that sum. That's one way to do it. The other way to do it would be to think about it in terms of a series, and the reason why I'm having you think about it in terms of a series and not just add these numbers up is so we can kind of tie something where we see, oh, I know what this means, to a more abstract mathematical language of the sequences and series. Well, so let's think about this. You've got 8 and you've got plus 2, right? Every time. So 10 plus 2, 12 plus 2. You've got a common difference. My a sub 1 is 8. And my common difference is 2. And so if I define this arithmetic sequence, that's what it really is, because you're adding 2 every time. I have 8 plus n minus 1 times d, which is 2. And so, to figure out my sum, I know I'm taking the sum from n equals 1, right? That's the number of my row, to whatever my number of rows is, and my sequence is defined by 8 plus.
For the following students.
And so when I define my sequence in here, I've got 8 plus n minus 1 times 2, and I don't need to simplify that at all. I just need to know how high it goes. Well, let's say I wasn't able to just draw this out and see the number of rows. I can always do this. I can always say, to find this, my top row is equal to 8 plus n minus 1 times 2.
Josh McLeod, please come to the...
And so when I solve this equation, I've got minus 8, so I've got 16 equals n minus 1 times 2. Divide by 2. So 8 equals n minus 1. And 9 equals n. Again, it's not like you couldn't do that and see that there were 9 rows. But what I'm saying is, what if it wasn't 24 seats? What if it went up to 1,000 seats? Then you're trying to figure out, how many rows there are, and counting them is an issue. And so when we find this sum, we can add up all of these numbers from n equals 1 to 9 of 8 plus n minus 1 times 2. When you find that sum, you end up getting 144 seats in that section. Okay, so that's kind of how we tie something we've already done in arithmetic sequence into a series problem, and kind of help ourselves out by having a little formula that works nicely. Next piece. That was a finite arithmetic sequence, right? A finite number of terms, meaning a known number of terms, and an arithmetic sequence because it went up by 2 every time. Let's say we've got this finite geometric sequence, and it's made up of these elements: a sub 1, a sub 2, a sub 3, and then all the way up to a sub n. And because it's a sequence, what I'm going to be doing is finding the sum here. And the sum of this finite geometric sequence looks like this. Sum of k equals 1 to n, because it's a known number of terms, of a sub k, which is equal to a sub 1 plus a sub 2, a sub 3, etc. Right? That's this. So I'm basically saying, I've got this series, I've got the sequence, and I'm making it a series by finding the sum. The sum is equal to the slick little formula, and I'm actually going to put it in red, because what you'll notice is this geometric sequence is going somewhere as we add them up. And so the sum is a sub 1 times 1 minus r to the n, where r is my common ratio, over 1 minus r. All right, so that's how this works, okay? And in this case, r can't equal 1. But I've got this nice little formula that's going to allow me to find the sum as long as I can recognize that it's a finite geometric sequence. Find the sum of the geometric sequence. So to get from here to here, you know, so on and so forth, how do I get there? Well, it's really 4, then minus 4/3, then positive 4/9, then minus 4/27. My common ratio is negative 1/3. And so when I go ahead and put this into my formula, the sum is equal to, from n equals 1, and my terms, so a sub n is equal to a sub 1 times my common ratio to the n minus 1, right? So if it's to the n minus 1, I've got 4 times negative 1/3 to the n minus 1. Well, I've got to figure out how many terms are there. Well, if 10 is equal to n minus 1, then n is equal to 11. So this goes from n equals 1 to 11 of 4 times negative 1/3 to the n minus 1. And so my sum is equal to a sub 1, so I'm using my formula here. A sub 1 times 1 minus r to the n. I put squared up here. It should be r to the n. R to the n over 1 minus r. And I'm going to plug in the pieces here. So this a sub 1 is my first term, and luckily they defined that one for me. So I've got 4 times 1 minus r to the 11th over 1 minus r. Plug in my r, 1 minus 1 minus, and I've got negative 1/3 to the 11th. And then on the bottom, I've got 1 minus a negative 1/3. When I plug this into my calculator, I get 3.0000 as my sum, okay? And it's got a decimal point, but we've got those 4 zeros, so we're going to round it to those decimal places, okay? That's exactly what we're looking at here. We've got this nice little formula, and as long as I can recognize that I have a finite geometric sequence, boom, that'll work. All right, infinite series. Let's talk about an infinite series for a minute. An infinite series goes on forever. You're adding up an unlimited number of elements. And so my infinite series looks like this. The sum of this sequence here, a sub n, from n equals 1 to infinity. Now, what you're thinking is, well, how could we find a sum for this? If I'm adding up an infinite number of elements, how could it possibly be that it goes somewhere? And what I want you to think about is this example here. I've got an infinite series where it's 0.1 plus 0.01 plus 0.001 plus 0.0001 plus 0.00001. Okay, and you kind of see what happens here. I'm adding a 0 every single time. Well, what does that mean? Think about what this sum would look like. Okay, and I'm going to rewrite this to kind of help you. I'd have 0.1 plus 0.01 plus 0.001, and I don't want to keep repeating that, but what you can see is this. And if you remember anything about decimal addition, you simply just add your columns, right? And so this 0.1 would be repeating. So I have this infinite series is equal to 0.1 repeating. When you do math frac on your calculator for fraction, right, what you get is that's equal to 1/9 if you put in enough ones. Well, how is this possible? This is possible because we're actually using partial sums. Here's what that means. As you get down to 0.000000001, that's actually really infinitesimally small. But it's infinitesimally small, but you're still adding it. So 1/9 is 0.1 repeating, but I only need a certain number of ones for my brain to kick in and say, okay, I see where this is going. The trend is going this way. That's what a partial sum is. Okay, the partial sum is the limit as n goes to infinity of this sum here from n equals 1 to infinity, right? Or I guess we're going to n because we're defining this partial sum. From 1 to n of a sub k, sorry, is equal to the limit as n approaches infinity of a1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n is equal to sum s. This is the partial sum. Meaning you add up a certain number of them and it's enough to show you where it's going. Okay, like that 0.1 example. Okay, and so each of the following series find the first 5 terms. Let's write them out. The first one is this, 0.3 plus 0.303 plus 0.003 plus 0.0003 plus dot dot dot. Where is that one going? B is this, 10 plus 20 plus 30 plus 40 plus, and C would be 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus, okay. I've got 3 situations here. What they're asking me to do is find the first 5 terms, sequence of partial sums, which of these series appear to converge. Let's look at this one up here. This appears to converge. This is like the 0.1 example, but it appears to converge to 0.3333333. The question is, okay, so that's 1/3, right? So 0.3 repeating is 1/3. The question is, how would I know that, only knowing 5 of the terms? You look at the trend. This is a partial sum, right? I'm looking at it, I'm thinking to myself, okay, I know where this goes. I see it going this way. And because it's going that way, I know when I add that other infinite part, the part that I am not writing out, this trend is going that way. Meanwhile, this trend right here, what's it doing? Well, this one's going to be divergent because it's going to keep getting up to bigger and bigger values. Okay, it's going to get up to bigger and bigger values, so it's going to be divergent. This one here, 1, negative 1, 1, negative 1, 1, negative 1. This is also divergent, and you're thinking to yourself, well, Mr. Saris, it doesn't get bigger and bigger. Well, think about it like this. It kind of goes off into infinity. 1, negative 1, 1, negative 1, 1, negative 1. This is kind of like what a sine curve would look like. Well, it doesn't have a limit. It's just going to keep oscillating into infinity. Okay, so a necessity of this whole deal is that we have certain conditions on what our series numbers can be. So it looks like this. We have a slick little formula for this one as well. K equals 1 to infinity. And it's of a times r to the k minus 1. Well, this is just the general formula for a geometric series. Geometric sequence. In order to find the sum, a can't be equal to 0, right? So it couldn't just be all zeros. And it converges, meaning there's a sum if and only if the absolute value of r is less than 1. Meaning I've got to have a rate, a common ratio, that's shrinking it. Right? So if it's the common ratio is, let's say, 2. If the common ratio is 2, it's going to be getting bigger and bigger, right? So that would be like 3 times 2 to the first, 3 times 2 to the second, 3 times 2 to the third. Okay? R is greater than 1. It's getting bigger and bigger and bigger. That's divergent. However, if I've got 3 times 1/2 to the first, 3 times 1/2 to the second, 3 times 1/2 to the third. That would be like, 3 halves. This would be like 3/4. This would be like 3/8. It's getting smaller and smaller and smaller. That's why that rate has to be small. Less than 1, okay? Here's my sum. The sum is, so if that's true, then the sum is A divided by 1 minus R. That's pretty simple. A couple of examples here. Determine if the series converges. A is this, the sum of k equals 1 to infinity. So we're dealing with the infinite series here, right? Of 3 times 0.75 to the k minus 1. And B, we'll do 2 examples. B is equals 1 to infinity pi over 2 to the n. Perfect. All right, let's take a look here. Necessary condition. Got to have A is not equal to 0. Boom, that's good. I've got to have my rate, or my ratio, my common ratio, okay, is greater than, or sorry, the absolute value is less than 1. So absolute value of 0.75 is indeed less than 1. Check. So sum is A sub 1 over 1 minus R equal to, okay, A sub 1 would be 3 times 0.75 to the, so my A sub 1, K would go, so to the 0, because K equals 1 goes in here. And then over 1 minus 0.75 is equal to 3 over, now this is 1 minus 3/4. So that's a fourth. So this would be equal to 12, right? Because 12, because I've got that fourth on the bottom. A good note on this is you're going to end up multiplying by some fractions. This one, got a test. Pi over 2 is about equal to 1.57, so divergent. Let's do one more example. I've got a repeating decimal here. Excuse me. So 0.234 is equal to 0.234, 234, 234, 234, 234. And so when I want to write it in fraction form, take a look here. I really have 0.234 plus 0.000234 plus 0.000000234. Okay, and that pattern goes on and on. Well, look at what I'm doing here. I notice that I'm adding 3 zeros every time. A side example would be this: 2,000, 2 million. To add 3 zeros on the end, I'm going to multiply by 10 to the third, right? To get 3 zeros at the front, I'm going to multiply by 10 to the negative third. So my common ratio is equal to 10 to the negative third. Okay, what I'm doing here is I need to have a way to write this in terms of a geometric sequence. Oops, spoiled the surprise. Yeah, it's a geometric sequence because I'm doing the same thing every time, but it's a multiply. My A sub 1 is equal to 0.234. So really what I'm dealing with is this is an infinite series from n equals 1 to infinity. And I define, so these would go together, A sub 1 times R to the k minus 1, or the n minus 1, however you want to slice it. So 0.234 times 10 to the negative third to the n minus 1. So that's my 0.234 times 10 to the negative third to the n minus 1. Well, check it out. I see that 10 to the negative third is less than 1. I see that. And so my sum is equal to 0.234 over 1 minus 10 to the negative third. Well, really that's 0.234 over 0.999. Can't put a fraction over a fraction, but I can make that 234 over 999. And when I reduce that, I'm going to get down to 26 over 11. How did I do that? I wrote my sum, or my whole 0.234 repeating, as a repeating decimal. What you're going to see is repeating decimals are going to yield fractions. Okay, they're going to be possible, but you just have to be able to write it as an infinite sum. Okay, thanks for watching, guys, and we'll see you next time.